In this video, we'll be having our brief introduction to logarithmic equations. I'm sorry, this is supposed to be functions. I beg your pardon. Alright, let's start. So, all we have to know about logarithmic functions is that it's the inverse of exponential functions. In other words, if we know that exponential functions has the domain of x is an element of all real numbers and the range, the y is greater than 0, the logarithmic function portrays the opposite of the exponential function characteristics. So as you can see here in this graph, if we have an exponential function that has a base greater than 0, we have a graph written this way. And in that case, when we convert this to logarithmic function, it's basically if exponential function represents f of x, logarithmic function represents f raised to negative 1 of x. I'm not sure if that's how you pronounce it, but I'm sorry if I may not be able to pronounce it correctly. But yes, I suppose this is familiar to you. Before learning this lesson, as far as I can remember, if this is rational functions, this is what we call inverse functions. That's everything that I could say right now. In terms of the forms of these two functions, for the logarithmic form, we have log, then we place the base as the sub-value, and the exponent will be at the other side, the y, and our x. Basically, when it comes to x, we don't really call it anything else, since actually, I'm not sure about the reason why, but whatever it may be, we just call it x. For the b, we call it the base, and for the y, we call it the exponent. When it comes to the exponential form, this is how it's written. The base is here, and the exponent is its exponent, and the x is at the other side. Now, this may seem unclear right now, but all it takes to be familiar with these forms is practice. So yeah, part of this lesson is the conversion of exponential forms into logarithmic forms and converting logarithmic forms into exponential forms. First, we'll be having these exercises. We need to know the general idea on how to convert exponential to logarithmic form. So, provided that we have an exponential form x is equal to a raised to y, all we have to do is to place y at the left side of the equation, place an equal sign, then write log, and just we know that a remained in the right side of the equation. We'll place it as a sub-value, and as for x at the left side, it will now be at the right side. So that's everything. Let's place this, let's make use of this general equation, general solving into practice. So, provided that we have 3 raised to 3 is equal to 27, it says here in the general guidelines, our x, assuming that it's 27 since it's a whole number, and a raised to y represents 3 raised to 3, we just swap the positions of the expressions within the equation. So 27 will be at the left side and 3 raised to 3 will be at the right side. Now, we know that y has to be placed at the left side. Y is 3 when it comes to number 1. So you place 3 and place an equal sign, write log, and we know that 3 will remain as a sub-value at the right side, and 27 will be placed in this fashion. Now, that's one example. Let's give me a few seconds to check. Alright, while we're waiting for the computer, I need you to solve in advance number 2, 3, and 4. Regardless of your answer, we'll be checking it anyways. There's going to be checking later. Okay, let's answer. For number 2, by the way, if you still have to answer, you still haven't finished these 3 questions, you may pause the video. We'll be answering right now. Okay, so 4 raised to 5 is equivalent to 256. All we have to do is to swap the values, place them, the value at the left side will be at the right, and the value at the right side will be at the left. That's it. Okay, so we place 256 is equivalent to 4 raised to 5, and place the exponent 5 at the other side, place an equivalent sign, write log, and place number 4, the number here, as a sub-value for log, and place 256, the number at the left side, at the right side. So that's it. Alright, let's move. Just box the answers. Let's move to number 3. Okay, swap the values again. What's in the right side will be at the left, and what's in the left will be at the right. Now, place the exponent at the right side, place an equal sign, write log, and the sub-value will be 2, the number that's at the right side, the base, and the number at the left side will be the number at the right side. Write it in this fashion. Okay, number 4. Let's swap the values again. There you go. This time, we do have to hang on. Never mind about what I'm about to say. For the exponent, we have x. Place an equal sign, place log. 1 over 3 will be our base for the log, and 27 will be our value at the right. So write it in this fashion. Okay, now we know how we could solve exponential forms into logarithmic forms. Now, this time we have to convert logarithmic to exponential. It's basically the opposite of what we did here. So everything that we have to know when converting from log to exponential is that we still have to swap the values. What's at the left will be at the right, and what's at the right will be at the left. After that, just have to acknowledge that the sub-value will always be the base at the left side, and what's at the left side, the value at the left side will always be the exponent, and the value at the right side will become our value at the right side. We'll just keep it as is. Basically, we just eliminate the log, and we move to the sub-value of log here as a base at the left side. And the base at the left side before will now become an exponent. And the 64 will be as is. That's it. Don't you think that 2 raised to 6 is equivalent to 64 after all? One thing that you can make sure to one thing that you could do to check your answer is that, of course, 2 raised to the number at the left side should be equal to the right side. You have to ask yourself, is 2 raised to 6 equivalent to 64? Well, yes, and therefore your answer is correct. For number 2, again, swap the values left and right. So 1 over 2 is equivalent to log 25, 5. I'm not really sure how to dictate this in verbal form, but for the sake of not really an experienced tutor, I could mention the sub-value. So log sub 25 and 5. Now, we suppose that what we have to do is place the sub-value here at the right. 1 over 2 will become an exponent, and place 5 at the right side as is. Now, 125 raised to 1 over 2 or 0.5 is equivalent to 5. I'm really sure of that. It's proven in the calculator. Now again, for number 3, swap values left and right. So there. Our sub-value for log will become our base at the left, and the base at the left before will become our exponent. So write it in this fashion. All numbers that are raised to a 0 exponent will always be equivalent to 1. That's one of the laws of exponents. For number 4, again, we swap the values. Left is right, right is left. Now, our sub-value 1 over 3 will be at the left side, and the base before at the left side will become our exponent. Write it that way. You reciprocate the base when the exponent is negative. So 3 raised to 2 is equivalent to 9, right? 3 times 3 is 9. So yes, this is our final answer. Alright. We're done with converting logarithmic to exponential and exponential to logarithmic. Let's move on to recognizing the two special logarithmic values or logarithm values, such that on these two special logarithm values, we have to understand that the base or b is not equal to 1. It shouldn't be equal to 1. Now, the first logarithm value is it's the logarithm of 1. Basically, log sub b times 1 is equal to 0 because b raised to 0 is equivalent to 1. For the second special logarithm value, the logarithm of b with base b. So it's written this way. Yeah, that's it. We won't be analyzing this too much right now, but you'll better understand it when we come to the examples. So I'll introduce to you the types of logarithms. First is the common logarithms, logarithms with the base 10 or the sub-value 10. This is the default base of the logarithm in the scientific calculator is 10. For binary logarithms are logarithms to base 2, so logs of 2. For natural logarithms, they are logarithms to base e. So again, Euler's number. I introduced to you about the Euler's number in the previous videos. You might as well want to check it out if you want to learn more about base e. Because the Euler's number will always be, it will be a common sight when you solve or simplify logarithmic functions. So, logarithmic identities. This is something that we have to know. Provided that, never mind. You just have to recognize these two equations. These are general equations so that we may be able to answer exercises such as these. So b raised to log, I apologize, I'm not really sure how to say these in verbal language. Let's just move on to the exercises. So provided that we have logs of 381 is equivalent to 4, move the values. Left values will be at the right and right will be at the left. So 4 is equivalent to logs of 3 times 81. We are trying to eliminate the logarithmic form. We're trying to transform this equation into exponential form. Therefore, we place the sub-value of logarithm at the other side, make 4 as an exponent, and we have 81. Prove that 3 raised to 4 is equivalent to 81. Use a calculator. It's true. Again, converting logarithmic to exponential. 1 is equivalent to log 7, and place 7 at the left side, raised to 1 is equal to 7. 7 raised to 1 is 7. For number 3, logs of 14, 1 is equivalent to 0. 0 is equivalent to logs of 14 times 1. we place the subvalue of logarithm at the left side as the base, and 0 will be an exponent. So everything that is every number, regardless of how big it is, when it's raised to 0, it will always land as a positive 1 answer. For number 4, again, switch values. 1 over 2 will be at the left side. Raised to negative 5 is equivalent to 32. Reciprocate. Actually, this is already the final answer. But for the sake of checking the answer, if it's really correct, reciprocate the fraction 1/2. It will be 2 raised to 5, which is equivalent to 32. Okay. This time, let's practice converting exponential forms into logarithmic forms. 49 is equivalent to 7 raised to 2. Pardon me, give me a few seconds to rethink of how to solve this. Alright, now we use the exponent from the right side. What will be the number at the left side? Place log, then 7 will be at the subvalue of log, and 49 at the left side will be at the right. This is the logarithmic form. For number 6, 1 is equivalent to 50 raised to 0. 0 is equal to log 51. Let's try to prove it. I hope you have your scientific calculator with you. Let's check. Log sub 50 times 1 is 0. Correct. Let's move on to number 7. 1 over 4 is equivalent to 4 raised to negative 1. Negative 1 is equivalent to log sub 4 times 1 over 4. Let's check with our calculator. So our subvalue is positive 4, and our base value for the log, this part, is 1 over 4. Yes, we have negative 1. That is correct. Okay, let's move to number 8. 2 is equivalent to 256 raised to 1 over 8. 1 over 8 is equivalent to log sub 256 times 2. Yeah, I suppose that's it. Let's check. Log sub 256 times 2 is 1 over 8. Correct. Right, we finished those exercises. Let's move on to another practice exercises for logarithmic functions. We have to find the value of x for each example. So we have to note first that finding x requires converting the provided equation form to its inverse. In other words, sometimes we have to convert exponential forms to logarithmic, or it could be converting logarithmic to exponential. Plus, in addition, we have to attempt to have both expressions of the equation with the same base. In the previous video about exponential functions, a brief introduction, we practiced how to have both expressions in the equation have the same basis. So it's the same objective, but the only difference is that we involve logarithmic functions conversion. Before we didn't have this, but now we do. Before we had this, and now we have this again. So let's move on to solving number 1. Right now, we could acknowledge that the equation is a logarithmic function since we see the log sign. We have to convert this to exponential equation first. So for our first step, of course, exchange values. What's on the left will be on the right. What's on the right will be on the left. Alright, 1 over 3 raised to x is equivalent to 27. With that, now, our logarithmic form is now an exponential form. So we've fulfilled this instruction, but now we have to attempt to have both expressions of the equation with the same base. This may seem tricky at first, but you have to know that 27 is, in other words, 3 raised to 3. And how do we make 3 raised to 3 equivalent to 1 over 3? I mean, the base only. excluding the exponent value. One technique is just copy what's on the left side. For the right side, you reciprocate. So isn't 1 over 3, I'm sorry, 1 over 3, give me a few seconds to place the expression on the calculator. Yeah, isn't 1 over 3 raised to 3 is equivalent to 27? Yes. Therefore, provided that we have written 27 in this format, we can now cancel the bases, and the exponents that were before will now be our bases today. So yes, x is equal to -3. That's our final answer. Right, for number 2, log sub 5x is equivalent to 3. What's on the left will be on the right, what's on the right will be on the left. I'm trying to be repetitive this time so that you may not be able to forget this technique. It's really an integral technique that you have to know. Okay, convert this to exponential. 5 raised to 3 is equivalent to x. This time, it's a little easy compared to number 1, since you don't really have to cancel bases anymore. X is already provided as a base, and we just have to simplify the number that's on the right. 5 times 5 times 5 is 125. So yes, that's it. For number 3, log sub x times 9 is equivalent to 2. Okay, switch values. Place x at the other side, raised to 2 is equivalent to 1 over 9. This time, since x has a square, an exponent of 2, we have to place a radical sign on both sides of the equation in order to eliminate it. So 1 is, in other words, 1 raised to 2, and 9 is, in other words, 3 raised to 2. So we have 1 over 3. Yeah, that's it. X is 1 over 3. For number 4, again, switch the values. 3 raised to 0 is equivalent to x. X is equivalent to 1 because 3 raised to 0, any integer that is raised to a 0 exponent will always be equivalent to 1. Hence, x is 1. Alright. I think I've said this before, earlier in this video. The default base of the log, this is what we usually see in the calculator, apart from the usual log, without the need of modifying the base. This is what we see. Default base is always 10. Now, I need your scientific calculator. You're going to have to need it right now. You have to type log sub 10 times 1000, log 50, and log negative 1000. Place that right now. You may pause the video while doing so, but I'll proceed. For letter A, our answer is 3. My hypothesis as to why the answer is 3 is that 10 raised to 3 is 1000. I may be proven wrong in this, but it's just my mere hypothesis. There may be other reasons why the answer is 3 when it comes to this specific question. Now for letter B, log 50, our answer is 1.69897, 3 zeros and 4. Now, depending on what your teacher says, you have to follow him or her when it comes to rounding off a decimal answer. As for my teacher, this is the final answer. Oops, sorry. It's rounded off to 3 significant figures. For letter C, log times negative 1000, we have a math error. This is, in other words, stating that the logarithm is out of domain. There may be a correlation when it comes to this expression, since as for exponential functions, it's no longer an exponential function if the base is less than 0. Most probably when it comes to this part of logarithmic functions, because this value is negative, we have no domain. I mean, the logarithm is out of its domain. Now, for simplifying the expressions, we do have to take in knowledge, commit to memory, the use of inverse properties. Exponential functions and logarithmic functions undo each other. Take note of the word undo. G of f of x is equivalent to logs sub b times b raised to x, which is equivalent to x. So whenever you see problems in this format, you can see that logs of b and times b, they are written in this fashion. They're cancelable. And hence, your answer will be x. When it comes to these kinds of questions, basically the inverse. So before we have log sub b times b. They can be cancelled. Now we have b raised to log sub b. They could be cancelled as well. They're basically inverses with one another. And we still get the value x. Now let's proceed to practice questions. For number 13, just copy the expression. Cancel. You know what to cancel? 8 and log raised to 8. Log sub 8. I'm sorry. So our answer is x. Number 13, the expression of number 13 follows this format. So b, assuming that b is 8 and log sub 8 is log sub b. For number 14, just copy the expression and we cancel log sub 7 and times 7, we get negative 3x. It's that simple. This time, for number 14, the expression follows the format of this, g of f of x. So log sub 7 is log sub b times 7, which is b. Okay, for number 15, let's just copy it. Log sub 2 and 64 raised to x. 64 can be simplified or can be rewritten as 2 raised to 6. So basically, we could rewrite the expression as 2 raised to 6x as 64 raised to x. And now, we could cancel. Hence, our answer is 3x. I'm sorry, 6x. Okay, e raised to ln times 20. By the way, you might be seeing this for the first time, the value of ln. They usually go along together with Euler's number, so please be aware of it. It's not really that difficult. It may be intimidating at first, but it's easy. You just have to find a counterpart value so that you can eliminate them. Hence, our answer is 20. What's equivalent to ln is Euler's number. That's it. And what's equivalent to Euler's number is ln. So they can be cancelable with one another. For number 17, for a while, I need a few seconds. Okay, this expression may be tricky at first because you don't know the sub-value of logarithm. But as said earlier, the default base of log is always 10. Therefore, in this problem, we rewrite the expression as 10 raised to log sub 10 times 4. Because when you, just like knowing that 1 or any number, it will always be raised to positive 1, right? For example, 72 is equivalent to 72 raised to 1, whatever may happen, regardless of the circumstance. In this situation, for log, the default is always 10, unless there's a stated base otherwise. But in this case, it's not that. So with this in mind, we can now cancel 10 and log sub 10. Our answer is 4. Okay, for number 18, log sub 525 raised to x. Similar to what we did in number 6, similar to what we did in number 15, we make the whole number 64 into 2 raised to 6. This time, we make 25 into 5 raised to 2. Therefore, we cancel. And our answer is 2x. I may not be able to explain this perfectly in verbal expression, but from how I solved the expressions, how I was able to solve the solutions, these may be able to communicate a better message to you, the audience. That's everything for this video. I hope you learned something. Thank you for watching.